科普中国。
A great pleasure to be here and continue my tradition of giving public lectures in China. Inspiring to see the level of interest in science in China and the dynamism and the increasing quality of scientific research that's being done. So my subject today is the great question that is at the frontiers of physics now, as well as frontiers of philosophy, to understand how and even if mind emerges from matter. Most scientists, such as neurobiologists working on human brains, make the assumption that mind does emerge from matter, that fully understanding brains will also teach us how people think. But we've also come to understand in physics that information is something that we should regard as physical. I'll be elaborating on that idea throughout this lecture, and that it can be embodied in several different, radically different ways. So not only is information and thought something that can be realized in the matter of brains, but can also be realized in other kinds of matter and in things that don't very much resemble human brains. All this suggests that mind can emerge from matter in several radically different forms, and that's why my title today is Strange New Minds. The first kind of strange new mind I will be discussing is something that you're probably all familiar with. This is the most mature technology I'll be talking about, but introduces the idea that mind emerges from matter in a very tangible form that nowadays people are very familiar with. In the case of digital computers, we know that everything they do, which in many ways resemble the action of intelligent entities, is based on manipulations of large numbers of zeros and ones. We know exactly how these strange new minds work because we build them. This understanding that information can be embodied as symbols, very general kinds of information can be embodied as just lots of zeros and ones, really starts with George Boole, an English mathematician and philosopher in the 19th century. He wrote a famous book called The Laws of Thought. You can find some earlier ideas like this in the philosopher Leibniz and even Aristotle, but it was really Boole who took it to a scientific level. And here is, in a simple case, the central idea that Boole propounded. One process of thought, one process of reasoning is logical deduction. And Boole had the idea that you could represent the truth of a statement by 1, the falsity of a statement by 0, and then have systematic rules for how you act on those zeros and ones to make new deductions, make new statements. So, for instance, if your statement A is true, so represented by a 1, if your statement B is also true, so also represented by a 1, then A and B, this means A and B, is also true, so that should also be 1. A or B is also true, so that's 1. Not A, over here, is false, so that turns into a 0. The rules for combining zeros and ones to make deductions of logic are called Boolean algebra. Inspired by this and by the needs of technology to do calculations that were useful to industry, Charles Babbage designed a more general kind of what he called an analytical engine, and Ada Lovelace worked very closely with him and was, in a way, the first computer programmer. She saw the possibilities for this machine and explained it to the world. This is a model of the analytical engine. This takes the idea that information is physical from the concept, from the realm of symbols, which George Boole realized, into mechanical manipulations. The setting of the different components of this machine, their little switches that go back and forth, and mechanical operations of the machine implement the rules of logic and can think, if you like. Alan Turing took the ideas that Lovelace and Babbage had developed in this very special and by today's standards small and difficult to use machine. He made it much more abstract, and so he tried to capture all kinds of thought, not just mathematical calculations or logical deductions, everything that people can think in terms of operations that can be made very concrete on zeros and ones. So, for instance, you can encode an image in zeros and ones by having the intensity of light described by a binary number with lots of zeros and ones, and different colors intensities also, and then manipulate the zeros and ones to produce a new image. Or you can process text, or you can do many things in addition to the logic and mathematical calculations that Boole and Lovelace and Babbage had in mind. An important thing to emphasize here is that although Turing's constructions were symbolic, he was a theorist, they were very, very explicit. So every step in the operation of this so-called Turing machine, this thinking machine, was very explicit. And so it could be read as instructions for the kind of machine you'd have to build in order to implement thought. And very importantly, Turing made convincing arguments, and other people also coming at the problem from different directions, converged on what seemed to be very different schemes for implementing thought, but turned out that all of them could be implemented using a Turing machine. So it became commonly accepted that any machine that could do the kinds of operations that Turing outlined, if they could do them sufficiently fast and on a sufficiently large scale, could do anything that a mind could do. This is called a universal computer, or anything that any kind of thinking entity could do. So this is a very, very powerful concept, that there's a universal kind of thinking machine. But I'd like to emphasize a very important question for physics and a very important question for philosophy, which perhaps young people who like to challenge authority and question received wisdom can think about, is whether it really is true that anything that's possible to compute, that's anything that's possible to think about, that anything that's possible to realize in the physical world really can be calculated by a Turing machine. This is a profound question of physics, and we don't know the answer for sure. Claude Shannon, who was a professor at MIT, took this to the next step when he made designs for doing the kinds of things that Boole and then Turing wanted to do, not in terms of mechanical gears and cranks, or in terms of pure symbols, but in terms of a much more modern technology that is electronic circuits. So these are called logic gates, and they are realizations of the logical operations that I showed you for Boole, but implemented now as inputs and outputs of electric circuits. So in one realization, which is very common, true is represented as a high voltage and false is represented as a low voltage. You put in 2 levels of electric voltage to one side of the gate, and with a properly designed circuit, out the other side comes the result of the Boolean algebra operation on the 2 things you put in. So if you wanted to represent and, you get A and B to be true, that is, your output to be a high voltage, if and only if both the inputs are high voltages. And so this becomes a problem in designing electric circuits to now realize physically the Boolean algebra. The actual electronic circuits are rather complicated. If you take courses in electrical engineering, computer science, you learn how to design these circuits. And Shannon's PhD thesis was based on being able to actually carry out the design of circuits that perform these operations. So this, for instance, is the logical circuit that just represents not. So if you input a high voltage here, a low voltage comes out this side, and if you put in a low voltage here, a high voltage comes out on that side. In the early days, meaning in this case, the period from about 1940s, when these ideas were first put together as part of the war effort, actually, and then until the revolution introduced by transistors, computers were based on vacuum tubes. When I was growing up, my father, who was an electronic technician dealing with early radio and television, filled up our house with these vacuum tubes. And so I got to know and love them, but they are, as you can see, rather big by modern standards. Compared to a modern computer chip, a vacuum tube is vastly larger, but represents only one element of one logical gate. They were also kind of unreliable, they got very hot, and so forth. But the first electronic computers were based on those. The modern era really began with the discovery of transistors and integrated circuits, so you could put lots and lots of logic gates in a small place. And by the 1970s, IBM produced its famous System 360, which still filled a room, but now was based on transistors, more sophisticated electronics, and magnetic tape to make memory. I'll say a little bit more about that in a moment. But for many years, this was a dominant and very useful technology. All the power in that room full of stuff and more can be realized in a chip that's maybe the size of your thumb. This is the inside of an Intel processor. You see that as a result of advances in physics and engineering, now you can have many, 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 many logical gates, all in a tiny object. This is what powers your iPhone, your laptop computers, a tremendous variety of modern computing devices that have become so central in everyday life and many industrial applications. It's worth remarking and standing back in amazement about what a remarkable device this is. So just to throw a few numbers at you, these are the specifications of that chip. The clock speed, so to do these logical operations, you have to say, okay, do one, then do the next one, then do the next one as a function of time, because the calculations march forward in time. The clock speed is 3 billion operations per second. That's called 3 gigahertz. Rate at which information is moving is similar. There is 10 to the, that is 1 billion times per second, information is transferred from one place to another. I won't try to give you the precise definition of this, but these thinking machines think fast. That's the main lesson. Human brains, their clock speed is more like 1,000 per second, so it's 1,000,000 times slower. The price is $999, much less than it would cost you to hire a student or an assistant to do calculations. But there are two things that are kind of limiting this technology. One is that it produces a lot of heat. So this is the thermal design power of that little chip, and it can produce, depending on how hard you push it, up to 130 watts. A human brain produces about 30 watts. Even though it's much smaller, it's producing more energy than a human brain, more heat. And a big challenge at the frontiers of computer technology is to get rid of that heat. Also, the size of the units is getting really, really small. This number, 45 nanometers, may not mean anything to you abstractly, but it's only a few times the size of an atom. It's roughly 10 times the size of an individual atom. So the little logic gates, the little pieces of electronic circuitry that are underlying the operations of this chip are not much larger than single atoms. The astonishing abilities of these chips, of these strange new minds, rely on powerful understanding of how matter works. So physics is great. To go farther, we need even deeper understanding of how matter works. Since smaller means faster and cheaper, the techniques whereby we've made smaller and smaller chips have driven these advances in technology. They are philosophically very interesting. You make machines that make smaller machines that make smaller machines. Unfortunately, it's more complicated than this, and again, requires many innovations in fundamental physics and deep understanding, but that's the spirit of the thing. And progress along these lines has been remarkable for many, many years now, for 50 years at least. Something called Moore's law has been operative. Moore's law is not a law, it's not a law of nature, but it's an observation about how the technology of digital computers has been evolving. It says very roughly that every 2 years, things get twice as small in linear dimensions, twice as cheap, and twice as fast. And as I said, that's been going on for several decades now. Now, getting a factor of 2 may not sound like much. As I'll show you in a moment, it adds up. This rate of progress, however, will be very hard to maintain for basic physical reasons. That is, present-day bits almost always involve either separating electric charges to get voltages, as I mentioned before, or alternatively aligning the spins of underlying objects, electrons normally, so that if you are wanting to encode your ones and zeros, which is always the task, in terms of voltages, what you do is separate charges like this. So you can have 1 if the high voltages if the positive charges are on top and the negative charges are on the bottom, and 0 being the opposite. That's one way to realize physically ones and zeros. Or alternatively, you can have directions of spins, which are all in one direction up or another direction down to represent 1 and 0. Now, you'll notice that in this diagram, I put in a few arrows or a few charges. That corresponds to the remark I made before that present-day sizes are getting down to a few times atomic sizes. So we can only have a few units in these basic realizations of the underlying zeros and ones. And the thing that's going to change Moore's law and change the nature of what we do and is very challenging if we want to keep improving the technology is that when we get down to 1 or a few spins or charges, the rules change. We enter the realm of what's called quantum mechanics or quantum behavior in physics. The quantum world is very difficult to work in. when you have only one charge or one spin, small fluctuations in the number change it completely. In the quantum world, fluctuations are everywhere. The nature of quantum mechanics is that we have probabilities we have statements not about certainties, but about probabilities, and this quantum world is full of fluctuations. Electrons can't be pinned down in position and speed at the same time, for instance. That's Heisenberg's uncertainty principle. So it's a difficult place to work in when your units are kind of moving around and hard to pin down. But as I will now elaborate, this strange quantum world is also full of promise. It opens up new possibilities if we work with it instead of trying to fight against it. Here we say we're moving from bits, binary digits, that's ones and zeros, to the quantum mechanical version of bits, which are called qubits or quantum bits. And this brings in the subject of now a new kind of information, not what Boole and Babbage and Turing and so forth thought about, which was just the zeros and ones as fixed quantities, but these kinds of fluctuating quantities inspired by the physical world, taken from the physical world. So the simplest two-state system, a qubit, so a single spin now, is very different from the classical picture of something that points either up or down, as I've already mentioned. It has this quantum uncertainty, and since we can't get rid of quantum uncertainty, we will have to learn to live with it. Let me say a few more words about the particular form this uncertainty takes. When we measure the spin of a qubit, so let's talk about the qubit as either a spin that points either up or down, we can measure the spin of that qubit in any direction. We can measure it in the x direction, or the y direction, or the z direction. And if we do that, we don't get a certain result. We don't get a definite result. As I said, things fluctuate. And in the principles of quantum mechanics, you learn that what you do find, is rather the probability for finding spin up versus spin down in each of the three directions, if you measure it. So instead of having just a choice, it's either 1 or it's 0, which is what we have for single classical bits, we need three numbers, three continuous numbers, also called real numbers, three probabilities to define what a qubit is doing, what it is, what state it's in. Instead of just having a choice, either 0 or 1, we have something that has to be described in a much more complicated way using three continuous numbers, real numbers, probabilities. So here's a little bit of an attempt to visualize something that's rather abstract, but emerges from the detailed study of physics. A bit is a choice of either a 0 or a 1. A qubit fluctuates around, but its state can be characterized by three numbers, which is also what you need to describe the position within a ball in 3 dimensions. So that already is a big expansion of the state space, the description of your fundamental units, which is forced on you by physics. Things get much crazier when we start to consider pairs of qubits. So if we want to characterize the state of these things, we can pick the x direction for both, or we can choose to measure the spins in the x direction for one and the y direction for the other, or y and x, and so forth. There are 9 possibilities. Each of those has its own probability, and then we could also leave one qubit alone and just measure the other. That introduces 6 more possibilities. And each of these, it turns out, in the principles of quantum mechanics, is described by an independent number. So 2 qubits are now described by 15 numbers, 15 continuous numbers. And so it goes. To describe the state of n qubits, we need 2 to the 2n minus 1 real numbers. Now, many of you will know how to interpret that symbol. 2 to the 2n minus 1, but in case you don't, let's see how it starts out. With 1 qubit, we need 3 numbers. With 2 qubits, we need 15 numbers. With 3 qubits, we need 63 numbers. With 4 qubits, we need 127 numbers, and so on. This gets very big very fast. In fact, these first few don't really give the sense of how fast it gets really big. But there's a story that makes this very vivid. This is a story about the origins of chess. When chess was discovered, either in Persia or India or maybe in China or somewhere else, don't take this story literally, the king was so delighted with this new invention, so enjoyed the game, that he wanted to reward the clever person who had invented it. So he asked this person, tell me what I could give you that would make you happy, and I will do it, I will give it to you. And the inventor of chess said, I'm a modest person, I don't really want a lavish reward, I just want some grains of rice. So, and I want to have something that is related to the game of chess. So, on the first day, give me 1 grain of rice and we'll put it in the first square. On the second day, give me twice as much, 2 grains of rice, and we'll put it in the second square. And the third day, twice as much as that. And the king said, that's ridiculous, that's so little, that's not worthy of your achievement. But the inventor of chess stuck with this request. The king started to comply with it. And at first, it was kind of paltry. You can see 1 grain of rice, then 2 grains, then 4 grains, then 8, then 16. But then it starts to get a lot bigger. And soon, the king was finding that his stores of rice were exhausted. He was very embarrassed. He could not fulfill his promise. So he killed the inventor of chess. But the lesson of this is that factors of 2, if sustained, lead to very rapid growth. This is called exponential growth. It's what has made Moore's law allow us to get from the kind of clunky machines that Babbage worked with to modern computers. And it's also what is the contrast between a quantum computer and a classical computer. A quantum computer, as you add more and more qubits, grows in capacity very, very rapidly, much more quickly than a classical computer grows as a function of the number of bits. These qubits are potentially extremely powerful. They open up vast computational spaces. But they're very delicate. In the original realization I mentioned to you, they would be single electrons or single spins, and those are easily disturbed, and these probabilities can be very easily disturbed by any kind of interaction with the outside world. And if you're encoding your information in terms of those probabilities, they're very delicate. So we need to protect these qubits from the outside world and from each other in order to maintain the integrity of the information. But on the other hand, in order for them to do any kind of useful work, they have to influence each other to implement the gates or other operations. And eventually, we don't want to just admire our quantum computer as a black box and be happy to know that it's thinking very fast and very powerfully. We want it to answer questions. So we want to be able to put information in and take it out. So we have to have a delicate balance between the isolation of the qubits, which is necessary for their integrity, and their need to work with each other, which is necessary for them to do useful things, and for them to interact with the outside world occasionally to take information in and out. So physicists and engineers are exploring several different ways to make practical qubits. This is a great challenge to physicists and engineers, and fundamental new ideas have been introduced, and I think more are necessary in order to live up to the potential of quantum computing. So I'll briefly mention the 3 main directions that have been followed or are being pursued. One is atoms addressed with lasers. Another is super circuits addressed electronically. And another is what they call anyons, which was mentioned in the introduction, which is computing with braids. The technology will surely evolve, just as digital computers moved from gears to vacuum tubes to smaller and smaller transistors, and from magnetic tape to modern thumb drives. We're at a very early stage. I would say we're at the level now in quantum computing of not even vacuum tubes, more like the analytical engine. So and I should mention that there are other alternative approaches which are less developed so far, but also potentially extremely powerful. That is to work with light instead of atoms or defects in solids, which is basically what these anyons are. So here, just to give you an idea of a very rough cartoon idea of the kind of things that people are looking into. This is an approach called Rydberg atoms. And in this case, your qubits are atoms that are trapped inside fields that hold them in place. So you have this array of atoms. You know where they are, so you can address them. You use a laser to excite. So ordinarily, if you don't do anything, they interact very, very weakly, so they're isolated qubits. If you want them to interact, what you do is excite them with a laser. Then the atoms can become very big, so-called Rydberg atoms. And if you make two of them big, they can touch each other and influence each other. And then if you do it just right, you can perform these kinds of operations that Boole and Turing told us to do. And then let them cool off by emitting radiation and go back and then keep doing it. So that's one approach. It's limited because you need to keep the atoms far away, you need to address with lasers, you need to be very careful about how you let them interact. That's why I say we're at the very early stages of these developments. But things will get better with any luck. There'll be a new Moore's law, Q-Moore law in the quantum domain that will have exponential growth from these modest beginnings. This is my friend Misha Lukin, who's built a 51-bit quantum computer. It's not a general purpose computer, so we call it a simulator. That's basically a Rydberg atom arrangement. I chose this picture to give you a sense of the size of what's involved and in the realistic frontier experiments. Also because Misha's a friend, and this was a nice picture I found on the internet. The circuits are more complicated to describe. I showed you even for a classical bit, and the simplest possible gate, the NOT gate, how complicated the circuits are. But physicists and engineers have become very, very adept, very skillful and experienced at designing complicated circuits, so that this is another approach that's being pursued. What makes this a quantum computer, what makes these qubits instead of bits, is that the circuits are very small and involve superconductivity in clever ways that allow you to realize effective zeros and ones that are individual quantum qubits. This is what a physical realization of this design looks like. This is the Google quantum computer. Recently, this has 53 qubits inside there. It's very cold. Most of what you see here is refrigeration. The actual computer is somewhere buried in here and is very small. And using this device, they recently announced that they've achieved quantum supremacy. That is, that this device has done something in a rather short amount of time, a few minutes, that classical computers, even the largest classical computers that are available today, rooms full of Intel chips, would take much, much longer to do. There's a dispute about exactly how much longer, but significantly longer. So they engineered a quantum system that's impractical to simulate classically. And I've showed you what it looks like. However, you should be very circumspect, very careful in interpreting this word quantum supremacy. It sort of suggests that quantum is going to be supreme and classical computers will be obsolete soon. That's not true at all. And in fact, the whole notion of quantum supremacy is kind of a funny notion. Because I know how to design a quantum computer using one atom that has quantum supremacy and actually solves a useful problem, unlike the Google problem, which is quite artificial. That is, consider a carbon atom, one atom. It contains 6 electrons and a nucleus and so on. And it's a very interesting atom. It's very important in technology. It's very important in our lives. We're made out of carbon. Carbon molecules are the basis of organic chemistry. No classical computer, or for that matter, no known quantum computer, can compute as fast as a carbon atom can how carbon interacts with light. So it can't compute what we call the spectrum of carbon. It can't tell us what colors of light will be emitted if you heat up a carbon atom. The message of this is that despite the word quantum supremacy, I think there will be an evolution in the technology, not a revolution, and we'll find that quantum computers will be useful for more and more tasks going forward, but not suddenly take over the world. Finally, the third method I wanted to mention, which I'm particularly fond of, and is particularly interesting as physics, is called braiding or anyons. The idea that you could compute by using knots really goes back to the ancient Indians in South America. They represented numbers as the number of knots and the kinds of knots, if you want to represent large numbers, inside ropes, and sent messages to each other and did calculations using these ropes. The basic concept here is that knots can get very, very complicated as you wind objects around each other. Anyone who's tried to do elaborate hairdos that involve braids, or even anyone who's tried to unsnarl their hair after taking a shower, knows that it can be very complicated to describe and control the patterns that you can get by winding things one around the other. So you can encode a lot of information in that. And if you have appropriate physical objects, circuits, or more advanced defects in solids that keep track of how they've been wound around each other, these are called anyons, then you can use those to store and process information. They keep track of their history in their quantum mechanical wave functions. My friend and colleague Jean-Wei Pan has pioneered some experiments on small-scale circuits that realize anyons artificially. So, as I've said, general-purpose quantum computers are still probably a long way off. However, quantum units that do useful things could probably come much sooner. In the classical computer world, people design things called GPUs, or graphical processing units, to do special kinds of operations that are useful in computer games. So being able to handle many, many simple computations involving all the pixels on a screen very, very rapidly, instead of doing what general purpose computers do, which is lots of different kinds of tasks, but because they have to be general, they do it much more slowly. There are certain kinds of tasks that quantum computers, even if they're rather small, because of the power of quantum qubits, should be able to do very well. And so a kind of hybrid design where you have a classical computer that does a lot of housekeeping and a lot of things that classical computers are already good at, but occasionally to do special tasks, calls on a quantum coprocessor, is something that is coming, I think, very soon, and Peter Zoller, who's in the audience, has pioneered in this kind of effort. For young people out there, there's a tremendous room for creativity and innovation in this kind of, in this domain of physics and engineering. So these quantum simulators you can think of as a modern or quantum version of wind tunnels. In the early days of airplane design, and still to a certain extent today, people would test possible designs by taking models without building a full-scale airplane, but taking them to a wind tunnel to simulate the conditions. Here we can simulate the conditions of, say, making a molecule on a quantum simulator without having to have a chemistry lab to actually make the molecule. Another way of saying it that may be more catchy and memorable is that we expect that quantum simulators, small collections of quantum bits, should be very good at doing quantum mechanics. So, whereas classical computers have a hard time doing quantum mechanics precisely because the qubits get very complicated very fast. So, if you want to calculate the properties of many interacting quantum units to make new materials or new molecules, it may be very, very helpful to map your problem onto qubits and use them as calculating units. And here are some of the specific ideas that have been used in the production of quantum simulators. This is a much easier task than trying to make a quantum computer that's a Turing machine and does everything that's possible. So far I've discussed digital computers and quantum computers as strange new minds, strange new ways of embodying information and thought in physical terms that are quite different from human brains. I'd like to discuss one more that's really been very impressive and successful in recent years, and is more closely modeled on how human brains work, but artificial and engineered. So these are called neural nets. The computers that I've discussed so far, the kinds of strange minds that I've discussed so far, are quite different in their design and concept from human minds. They deal with symbols or abstractions and physical elements that are quite different from what you find inside a human skull. Biology works differently. It uses much slower units. It has much higher connectivity among the units than we have in electronic computers or any existing design of quantum computers. And it has a layered architecture and massive parallelism, which again are rather different from what you find inside computer chips. So here is inside the human retina, which is still today our best image processor, in many ways far better than any computer. This is what you find inside the cerebellum. This is the unit of the brain, which is a kind of small bulb that hangs back here. That's specialized for synchronizing our muscles and making our motions smooth. And again, it has this kind of layered architecture. No one understands how it works in detail, but it's very powerful, very good at what it's doing. No robot that humans have designed can move nearly as smoothly or efficiently as humans move themselves without even thinking about it. So, although the units are small, although the units are slow and not as reliable, not as precisely machined as what you find inside artificial computers, it works very well. Here I am. It works pretty well. And here all you are. So people have tried, inspired by this observation, this experience, that these kinds of very different architectures can work very well to implement thought, to build a third kind of strange new mind. The basic building block here is not a unit which is either 1 or 0, as in classical computing, or its quantum generalization, as in quantum computing, but what's called a neuron. And this is a neuron. What you do is have several inputs, which are numbers, several weights, which are also numbers, and then you multiply or otherwise process the inputs based on what the values of the weights are, and take that input into your neuron, and then the neuron, based on the value of that input, produces an output. And then you can keep doing this. You can use the output from one kind of neuron to feed the next layer of neurons. So this is a simple, idealized model of how actual biological neurons work in terms of electrical signals coming into the neuron and producing an output signal. It has the advantage of being something we can design and manipulate mathematically with precision. The great discovery in this field, which went in several stages, but recently has become a working principle that's become very, very refined and powerful, is that networks of these simple neurons can learn. They can learn by changing their weights so that they perform better and better. Here's the basic idea. So suppose your neural net takes inputs by looking at a lot of images and encoding what they see, and then sending that message to another layer of neurons, which then propagates their output to another layer of neurons, which then goes to outputs, which can be interpreted as a message telling you what the information encoded in the original image was. So for instance, you may have a neuron that fires if the original image contained a cat, or a human being, or a face of a certain kind. Okay. Now, suppose your image contains a cat, but your output doesn't, or says only with certain, then there's an error. So how do you do better? Well, the neuron knows that it's produced the wrong answer. You have an instructor that tells you whether you've gotten the answer right or wrong. If there's an error, this neuron tells the earlier layer of neuron, which gave it its information, that it made a mistake, so it should change its weights so that it would have done better. So that neuron says, okay, I'll change a little so that I would have given you a better answer. And then this guy also was wrong, so he blames the guy above and tells her that she made an error. This lady says, oh, I made an error, so I could have done better if I had different weights. I'll change my weights a little. And you keep going. This is a very, very simple idea. It's called backpropagation, and it's a way of learning from your mistakes systematically to improve the weights that in such a way that they will give more and more correct answers and fewer incorrect answers. This has been carried out not to much more elaborate networks. It's called deep learning. So this led to several very impressive successes. Deep neural nets have become very good at recognizing in images faces or cats. They've also, remarkably, learned to do things that were once thought to be the pinnacle of human intelligence, such as play chess, play Go, play StarCraft at superhuman levels. Let me just say a word about the chess example, which I find particularly impressive, probably because I know more about chess than about Go or StarCraft. Chess is a game that's been studied intensely for centuries and has a literature that's vast, and human players have devoted their lives to it, thought they understood the game very profoundly. But a neural net was given just the rules of chess, and by playing against itself and using these strategies of deep learning, within a few days, actually a few hours, got to be so good that it's far better than any human player ever was, and far better than humans could teach classical computers in other ways by programming to perform. This is a humbling idea that we have created things that do tasks that we thought were kind of the pinnacle of intelligence in some ways, and do them so much better. If you don't think games are important, they've also learned to perform better than any programs or humans at problems like determining from the chemical structure of a protein, its DNA code, how it will fold and what shape it will take. So I've emphasized that these networks using backpropagations were used for all these tasks, but they're not the most capable. Our brains have much more complexity, and their excellent performance is enhanced by these kinds of feedback. So instead of just having a one-way flow of information, you have information that goes back and forth and is reprocessed. The network looks at itself. In other words, to put it in plain language, it's thinking about what it's doing. We think about what we're doing. Deep propagation networks don't really think what they're doing, they just do it. They don't introspect, they don't examine their own performance. To this next level of thinking, we'll need to get beyond backpropagation and think about networks that look into and direct other networks. Okay, so thinking back on our own experience, it's very plausible that besides sensors that monitor the external world and bodily states, we have modules that monitor, predict, evaluate, and direct our internal brain states that look into what we're thinking. In other words, the experience we have that's called consciousness, that we think about what we're thinking about. This might be closely related to and might essentially be consciousness. In fact, there are fascinating experiments pioneered by a man named Benjamin Libet, but now this was already in the 1970s, I believe, followed up by many, many other sophisticated experiments that point to this kind of idea that what we experience as consciousness is not something that makes decisions, but something that looks at what's going on in our brains and reports on it. So let me show you this beautiful experiment, which changed how I think about myself and the world. So it's a very, very simple experiment. This is a cartoon version. You have the subject is given a very simple task. The subject is asked to do two things. One is every once in a while, whenever he or she wants to, press a button. But also, look at a clock, record, when you made the decision to press the button. Okay, so you decide when you can decide you're going to press a button, and you tell when you've decided. That's the experiment. Well, the third component of the experiment is that the subject is in an electroencephalogram, a machine that monitors the brain activity. What is found is that people say they've made the decision. When people report they've made the decision, about 0.2 of a second after the brain activity that's ultimately going to result in the button being pushed has started. So the activity that leads to the button being pushed down is actually not the consciousness of making a decision. That's actually a report of the deep structure of what's going on in the brain. The deep structure precedes the conscious awareness. And as I said, there are many experiments now of this kind with many refinements in modern technology, and all consistent with that idea. So, to put it again in plain words, if these ideas are right, a big step in artificial neural nets will be introduced consciousness. On the material side, we should also take lessons from biology. We should introduce self-reproduction. The way brains are produced is by cells that take advantage of exponential growth and double and double and double by the process of mitosis, that is by self-reproduction and by self-assembly. The process by which human brains are made is quite different, in some ways much less expensive, and certainly much more fun than the way that artificial brains are made, and it's been produced by evolution, but can be mimicked artificially and may be made on a bigger scale, faster, and so forth. But this is the physics and engineering of the future. So this is a crude idea of self-reproduction, but John von Neumann, the great mathematician and sort of visionary already, who, by the way, pioneered the so-called von Neumann architecture, which is what underlies all modern computing machines, produced a book outlining how you would make a self-reproducing machine, and biology does it, both at the level of organisms and also at the level of brains. So let me very quickly summarize and say a word about the future. Strange and powerful new minds of several kinds are on the horizon. Young people who want to change the world, the doors are open for doing that. In sculpting them, there's enormous scope for creativity. Physics and physicists have a lot to contribute. Thank you.